Okay, so we just put your density formula. Yeah, I think for all practical purposes, it would be a good idea to have these done tomorrow because we have gone over enough information that, let's say, out of those, what, there are 10 problems on there, right? So 9 of them is new information. That 10th one is a review from 2 chapters ago. And so that leaves 9. 2 of them are density problems, so then that leaves 7 of them. Hopefully we got those figured out. Then those last 2 deal with densities, and then the last one is a review. So looking at this, what problem may we have? I think once you get it set up, it's probably the hardest part of that when it comes to calculating the density of a gas. Would that be correct?
Yeah. Let's do 5.
Okay, so what does number 5 say?
The density of a gas is found to be 2.0 grams per liter and 1.58 atmospheres and 27 degrees Celsius. What is the molar volume of the gas?
Okay, so we got to have some other information here. Oh, no, we don't. Okay, so as we're looking at this formula, obviously D is density. That's going to be measured in grams per liter. P is pressure, so that needs to be in atmospheres. This is a constant. Temperature is degrees Kelvin. And then this M is a molar mass, so grams per mole.
So density, so D stands for density, M stands for mass, P stands for pressure, R stands for constant temperature.
That is correct. Now, when we say M is for mass, that's half right. It's molar mass. Okay? So once you get it to this point, hopefully it's downhill. After that, would that be correct in, although I just have grams per liter, it's 2, correct?
Yep. Constant 0.08. It's the 22.4 divided by.
Do we watch the science channel when we miss class? But when we're asking that, the answer to that would be no. Okay, so when it comes to this constant, okay, if we were to divide, okay, for every 1 mole at STP, what volume is that? It's 22.4 liters for every 1 mole measured at STP, and what's the temperature for that as well when it's at STP? So if we divide 22.4, so why would we not be concerned about pressure at STP? Because it's just 1, where obviously if you divide or multiply by 1, you're going to get the same thing. So if we take 22.4, if we divide that by 22.4 divided by 273, what do you suppose we get when we divide them to? 0.08205, which gets rounded up to 0.0821. Because when we're measuring gases at STP, that makes things really, really simple. But not all gases are measured at STP. So then the ideal gas law takes that into consideration, that any pressure, whether it's 3 atmospheres, any volume that may be 45 liters, any temperature with that constant in mind relating back to STP allows you to find any one of those variables. Yep. So with that, do we need any further context? Because once you have it in this form, well then we want you to do what the formula tells you to do, which is set equal to what goes on top of that fraction. Okay, so we're going to take 1.50 times what? Times m, and then what goes on the bottom?
20, well,
Okay, so that 300 means you're taking 273 and adding 27 to give you 300. So what would be the best way to get M all by itself? Cross what? Our I's, our T's, our fingers, what? Yeah, we can put 1 under here. That's fine. So, what are we taking 2 times? Okay, so if we're taking 2 times 0.0821 times 300 equals 1.50 M. Would you agree with that? Okay. So then, go ahead and multiply those out, which would mean 600 times 0.0821. And if we divide that by 1.5, the molar mass equals what? Okay, so this is going to be an unknown gas, so we really don't know what it is, but it is, okay, and maybe, I just glanced at, yep, 32.84. So it could be fair to say that maybe there's just some slight impurities in with this gas. What would you guess that it's possibly, what could possibly have a molar mass of 32 grams per mole? Oxygen. You would be correct, but it's got to be a gas. Okay? So in this case, maybe this is oxygen with a little bit of impurity in there, meaning that 0.84. Okay? So are these problems, they may seem difficult, but once you get them into per se writing down what you know and getting into the fraction, then it's just a matter of using your algebraic skills. How are our algebraic skills? Okay? Very good. So do we need to go over any more about the ideal gas law? No, 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 no. Okay. Well, as we look what the column says for Monday, it's the dreaded what? Gas stoichiometry. In other words, worksheet 3. It's kind of like Hercules. It's Greek mythology. Is that Herculean tasks, if you want to call it that? That each one is a little more difficult than the next. So, how many of you would agree that dimensional analysis on worksheet 1, everything's measured at STP? Not too bad. Now, not all gases are measured at STP, so you need the ideal gas law. Maybe a little more difficult. Now comes the tough part. Okay? And that's quite possible. Because when you use the term stoichiometry, that means you have to have what somewhere in the problem? Yeah, you need chemistry. You need a balanced chemical reaction. Okay, which is just what you're going to say, correct? Okay, so one thing to do would be, let's possibly look at page okay. What about moles to grams? Well, then you're going to put your mass on top. Is that bad?
Do you have one mole? Yeah. Then mine's fine. Okay.
All right. Yes. Grams per mole. Says it right there. For density, it's grams per liter. Okay. All right. Are we good? Okay. So to answer your question, and if you could repeat that, how do you convert moles to grams? Is that what we said?
Yeah, we got.
So we're good.
Yeah.
All right. I'm deciding that right now.
So our test on Friday, is that over worksheet 1, 2, and 3?
No.
Just 1?
1 and 2.
Okay.
Yes. All right. Now we're mean, but we're not that mean. Would you agree with that?
Yeah.
Or we could say mean but fair.
Yeah.
Would you agree with that? Okay. So let's go ahead and look at page 382. Okay, there is a sample problem H that you could read on page 382 should you choose to. Okay, but one of the things that you would note that it has up there in that sample problem, it's talking about the given information and then the unknown, but when it says the analyzed portion, what does it say you have to have first? A balanced chemical equation. And that is why, how do you suppose we get the term gas stoichiometry from this? Because what is reaction stoichiometry, do you think? Yeah, and it could be anything from sulfuric acid reacting with a metal, anything that's unrelated to gas stoichiometry. It's just reaction type. Now, you have to have a gas somewhere in this problem. Whether you're starting with a solid and converting that to a gas, or if you have a gas, you're converting that to how much of a solid would be needed. The main idea, gas, has to be somewhere in that problem. So, how many of you, as you're looking at the ideal gas law, how many of you really, really like the ideal gas law? One. And that's fine. How many of you like dimensional analysis better?
Wait. Dimensional analysis, what is that?
That was what you just handed in.
Yeah, that was better than this one.
Okay?
Why are you guys not raising your hand?
All right. So, on page 382, okay? Assuming, okay? Assuming this, all volume measurements were made at the same temperature and pressure, what volume of hydrogen gas is needed to react completely with 4.55 liters? No, I don't want to use that problem. That's not a good one. Sorry. Unless we were to change that. Well, we can continue. Volume of hydrogen gas need to react completely with 4.55 liters of oxygen to produce how many grams of water vapor would be a better way of looking at that. Okay? Because whether you're looking at hydrogen or whether you're looking at oxygen or water vapor, any one of those substances, those are all what? Those are all gases. That's right. They're not Two of them are, but one of them is not. Okay? And since they're made at the same temperature and pressure, we're going to say that's measured at STP. Okay? So, what that means is, what is hydrogen? And we're combining that with what? And gives us what? And water vapor. Okay? So, we got a balanced chemical reaction. So then, that means you got to take that step. Okay? And then, I did that wrong. I put the coefficient in the wrong spot. But you would have caught that, right, people? Okay? So what we want to know is how many grams of this can be produced. And it says we're starting with 4.55 liters of this. Okay? So now, do we still have ideal gas law people in here that really, really, really like that? Okay, so which way of solving this would you like to see first? Dimensional analysis or the ideal gas law? Okay, so the ideal gas law. We can make these presumptions. What would the pressure be at STP? What would the volume be? Okay, because that was given then. Okay. And then R and then T, correct? Okay. So with this, since I'm shooting from the hip here, I just want to make sure that we're doing this correctly, because we need to change that to grams then of water. Okay. So with this, okay. Next thing we want to do then is solve for, well, how many moles of oxygen would that be? Okay, so with that, okay, so what I mean is plug those into our equation now, because we've got the ideal gas law right there. Okay, so for every 4.55 liters, we get 0.0821 times 273 times N, correct? Okay. So why did I not write anything else besides that on this side of the equation? Because it's still 1. Okay? So upon doing so, once we do that, when it's at STP, we already know we got 22.4 right here. Correct? You can make that presumption, 0.0821 times 273. What a coinky dink, 22.4, right? That's what you got? Well, we're going to use 22.4. So 22.4 N equals 4.55. Okay? How do we get N by itself? Okay? So 4.55 divided by 22.4, that gives us N equals 0.20. Mole of what substance are we in right now? Oxygen, because we haven't converted it yet. Okay? But there's no way of getting around dimensional analysis completely. Because now that you've got it in moles of oxygen, now you can convert it to what that we did 2 chapters ago. We can convert it to grams now. So if you really, really understand this, I wouldn't have to go any further, because all of this is a repeat of what we've done before. So let me ask you this. Is anybody lost? Well, okay. So if that is the case, okay, 3.60. 3.60 grams of water, right? You got double that, didn't you? Yeah, because it needs to be doubled.
Is that right?
You're right.
Oh my goodness.
Well, why are you doubting yourself?
I don't know.
It's possible to make mistakes, isn't it?
Sure is.
So we're just seeing about that. Okay, so as we look at this, if we take 0.20 mole of oxygen, okay, so there's no way of getting around that. It's just like taking moles of this substance now, because we just solved for it. So for every mole of O2, we would get moles of what we want. And remember, this is a mole ratio. So anytime you see a mole ratio, what do you need to do? Got to go back to your equation. Okay? Which then means, why is this step so important? It allows you to change what? What you have into what you are, what you want. So now we've converted our moles of oxygen now into moles of H2O. So for every mole of H2O, you're going to get what? Okay? I was just seeing if anybody fell in the trap. But you didn't. Because if you just took 0.20 times 18, that gives you 3.6. So when you said that's not what I got 7.2. You got to go back to your balanced chemical reaction and double that. So if you're working on these and you find out, well, I didn't get that, I got half as much as you got, or I got twice as much as what you got, chances are that's where you made a mistake. So that is the ideal gas law way. How many of you think that's horrible? How many of you would rather just get rid of this all at once? Dimensional analysis will do that. You had said earlier you liked that better.
I do, but not like with this stuff.
Okay. So, we can safely say we should get 7.2. Okay? So now, let's go ahead. We got to go all the way back to the beginning because we're disregarding this. We're getting rid of that ideal gas law. Okay? Because remember, if you are an ideal gas law person, this is how you would set that up. Okay. So, if we've got 4.55 liters, okay, and that's of oxygen. So, how are we going to get that volume to a mass? How do you get rid of this liter and get it into moles, do you think? It's at STP, remember? So, if we put 22.4 liters of oxygen, that gives us one what on top? That gives you a mole of oxygen. And we can make that intuitive leap or jump because this is measured at STP. So now we're in moles of O2. But we don't want O2. We want H2O. So, how do we get rid of this mole of O2? You have a mole of O2 on the bottom. And then what would we put on top? We're changing what we want into what we're looking for. Nope. Because we want grams of water. We're still in oxygen yet. Okay, so these liters are gone. These moles are gone, but don't forget, what do we got to look back in this problem? The coefficients. Now these moles are gone. Now we're in moles of H2O. Now for every mole of H2O, how many grams do you get? What do you suppose you're going to get when you multiply all them out? Okay, so how many of you like this way better? Now, you can't do this every time. The only time we can just use pure dimensional analysis is when the gas is measured at what? When it's measured at STP. That is the only time. Okay? Actually, unplug this. Hopefully that doesn't affect the recording of it. So we'll plug it back in. There. Okay? So, it's going to tell you it's measured at STP. Okay? So keep in mind, if it says in a chemical reaction, it gives you like 0.89 atmospheres at, maybe it says 210 degrees Kelvin, well then you have to use the ideal gas law. But if it's measured at STP, you can use either way, but dimensional analysis is a lot easier. Because why would you think this is much easier than using the ideal gas law? There's less chances of making a mistake, for one. Because this is not easy. I see a bunch of you sitting like this, and just looks like you're totally worn out. We just had 4 days off. Well, we're away here for 4 days. Maybe you didn't have 4 days off. Okay, so what did we do yesterday? Okay, now, okay, so I think this would just be human nature. If we said that today was another spring break day, would you be recovering or would you be at work then? Do you think? Oh, okay. I mean, that's fine, but one of the things to keep in mind, when you get off into society, you're not going to have these multiple days off, and it's not going to be, oh, I just need time off. And hopefully when we look at this, these papers, okay, does it say it's due tomorrow? No, you've got time. You've got time to work on these, okay? But I guarantee you some of these will get to be more difficult because it may say something like, what is the mass of iron 3 oxide produced from 2.5 liters of oxygen gas? Remember, you have to have a gas somewhere in this problem. And it has to have to say it's measured at STP. But if it's not measured at STP, well then you have to be given the pressure, the volume, and the temperature. Okay, so whose head is spinning? Nobody? Either we don't know yet, or I really, really hit you people really hard, metaphorically speaking, hit you really hard. That is correct. Because even if you're using the ideal gas law, you still need to use some dimensional analysis. But it's just easier if you use dimensional analysis in that case. Okay, so now there's some individual questions. Do you think everyone could benefit from this? Okay, is it a certain number?
Yeah,
Number 9 on worksheet 2.
I guess just what's the kilograms?
Okay. Well, to me, that would be 0.004 kilograms. Then to change kilograms to grams, you multiply that by what? 1,000, so that gives you 4 grams, correct?
So kilograms to grams is you multiply by 1,000.
That is correct. And 675 torr, what is torr?
Volume.
Torr is not volume. Torr is pressure. So it's also the same as millimeters of mercury. So you need to take 675 and divide that by what? 760. That gives you your pressure in atmospheres. What gets divided by 1,000?
Kilograms you multiply by 1,000.
Okay? All right, we will pick up with this information tomorrow.